So now let's talk about critical density. We said that the critical density is very important to know the evolution of the universe eventually, and we stated that the total energy of that mass at the edge of the gas cloud that we're going to consider as the universe in a way is equal to 1/2 mv squared, which is kinetic energy plus potential energy, and the type of potential energy is gravitational potential energy. So that has this equation that we remember, gmm over r. Now, this is the starting point to get to something that tells us how much this mass will keep moving forever, meaning that the universe will keep expanding forever, or will stop at some point, or actually will come back and shrink or squeeze the universe into what is called the big crunch. So let's keep that in mind. We're going to analyze what happens if E is greater than 0, what happens if E is equal to 0, and what happens if E is smaller than 0, right? So this larger than 0 is it never stops. E equals 0 is it stops at infinity. That means that it's gradually slowing down until it has no energy, but that only happens at infinity. That's when these two terms are equal, when the kinetic and the potential are the same. And then if it's equal to 0, it's what we call, well, the scenario of the big crunch. That means that it will come back to zero size. Okay, so we want to know what the role is of the density in the middle of this. So that means that we're going to have to somehow include the density of the universe. So we're going to take ρ as the density of that cloud, and that cloud, which represents the universe, has density that it's equal to its mass over its volume, obviously, and then the mass of that cloud, the mass of the universe, will be the density times the volume. Let me make this V a little bit bigger, so it stands for volume, not for velocity. So then we're going to use that, right? We know that the volume of that shape is the shape is a sphere, so it's 4/3 pi r cubed. And what is going to happen is that well, the mass, it's going to be something like this. So let me put it like this: E will be equal to 1/2 mv squared, and then minus g, and then the mass, which is big M, rho 4/3 pi r cubed. That will be the big M, then the small m, and time and over r, right? That's what the equation would tell us. Now, we have included the density of the universe successfully in that equation, but we're missing something, and what we're missing is something in this other term that would help us simplify things a little bit. So we know also that the speed, say, if we're at the center of that sphere, then the velocity of that point at a distance r from the center, and if we consider ourselves being at the center of that expansion, then that velocity will be given by the Hubble's law. So it will be ho times the distance, but the distance is precisely that r. So I can incorporate that into my energy equation and say that this is 1/2 m h0 squared times r squared minus, and I'm going to try and rewrite this as g rho 4 pi r squared m, right, over 3. So I think I got all the terms there, and obviously I'm doing that because this r cancels with this and gives you a 2. So I get g rho 4 pi r squared m over 3. Yes, that's right. And what we get is this. We get, I can factor some terms here. I could say something like, and I'm just going to do it the usual way to get the number that we're trying to get. 1/2 mr squared is the factor that I'm going to take out. And if I take the first term, that means I'm going to get only h0 squared, and then minus, and I'm going to get something a little bit more complicated here. Well, the mr squared will go out, but since I took this 2 down here, since I took it out, I need to double what I have inside. So 8 pi, the r squared and the m went out. I have the rho and g, that's how I'm going to write it, divided by 3, right? And that's what I have. Now, here's the thing. The mass of the object, this little mass here, is the mass of the object that we're considering is moving at the edge of that sphere. So that mass obviously will not be 0. The distance, the radius, will not be 0. So if this whole equation, remember, we want to analyze these 3 conditions. Never stops, stops at infinity, or we have a big crunch. And the critical case for that is when this becomes 0. So we can know whether this actually is 0 or not. And to do that, what we're going to say is, okay, let's analyze this term, because this term here definitely is not going to be 0. If something is or has the possibility of being 0, is this other term, depending on how those constants there relate. So depending on how this relates, h0 squared, 8 pi rho g over 3. So if this thing is equal to 0, then we have the density that tells us that it stops at infinity. Now, when does that happen? That happens obviously when h0 squared is equal to 8 pi rho g over 3, which leads to a value of the density of the universe that will be high enough to stop its expansion, but only at infinity. So 3h0 squared over 8 pi g. Now, h0 is a known value, pi, g, 8, and 3, they're all numbers. And when you solve this, you're going to get a value of around 10 to the negative 26 kilograms per meter cubed, right? And that is what we call the critical density of the universe. Now, this equation that I've just put here, 3h0 squared over 8 pi g, is something that you need to be able to derive. This is in the booklet, but you could be asked to do this derivation to get that that's a critical density of the universe. Now, what you need to remember is that what you need to remember, I was just checking the time. You need to remember that we start from just an analysis of energy, a regular analysis of energy, where we're talking about the energy of that mass at the edge of that sphere that we're considering as the universe. And then after that, we do kinetic plus potential, and we start working with the density of the universe to include it in the mass term up here. And then we go with Hubble's law, because that object at the edge of the universe, in that case, in that sphere, is moving at a velocity that can be predicted based on Hubble's law. So that's why that v is used here. And then when we put all that together, we realize that we have this expression here. And this expression here is what is going to tell you the critical, or like the three different cases. Obviously, we're going to solve for when this is equal to 0 and then analyze the possibilities of that. So when is that equal to 0? That is equal to 0 when this happens, when the density of the universe equals that value. So let me just add another page here. And so we're left with this, the density of the universe, the critical density for which that term becomes 0 is this 8 pi g. So when that happens, that means that the energy of that mass will become 0, but that will only become 0 after it reaches infinity, because that is the only point when the gravitational potential energy is 0. If you look at the equation, it goes with a 1 over r, and that term 1 over r can only become 0 when it's at infinity. So if this is to become 0, it needs to happen at infinity. So that's what that means. Now, what happens if the density is larger than this value? If the density is larger than this value, then we have the case that E is smaller than 0, and we have the big crunch. That means that the universe will that means that the gravitational potential energy will let's say take over, and gravity will just bring everything back together. And then if the density is smaller than the critical density, then we have the case E is larger than 0, which means that the kinetic energy will dominate, and we reach the scenario where the universe expands forever, and actually never ever stops. So E greater than 0 happens when the density is smaller than the critical value. E equals 0 happens when the density equals the critical value, and E smaller than 0 happens when the density is actually, is larger than the critical value. And what you need to be aware of is those three conditions, right? The conditions for which the energy will be equal to 0, greater or smaller, and obviously the corresponding relation with the critical density. Oops, sorry for that. The relation with the critical density. Okay, let's go to see if you have questions.